Morning.
Maar dat is
Volgens mij heel veel dingen. Achter de ventilatieopening. Het kan best zijn dat iemand anders ook.
2 à 4.
Dus in het slot.
Wat zei je? Ik ga even
So, welcome everybody. It's time to start. So today we'll be talking about MD simulations, and I've seen many of you have read the chapter. Before I start, are there any questions about based on the chapter about molecular dynamics of proteins?
Yes, a lot. But like
A lot, okay. Then let's start with the lecture. I just realized that the lines are closed. Oh, yes. That's weird. Okay, so we'll do molecular dynamics mainly. So it's about simulations. It's about basically a model of how proteins move. And we've talked about protein motion and dynamics and flexibility and function quite a lot during the course. That is sort of the one of the main themes of the course. I've actually been thinking of putting it in the title of the book because we call it Structural Bioinformatics, but maybe it's also more about protein structure and dynamics. So we figured out how to combine that with bioinformatics. And because we're talking about dynamics, we'll also touch upon thermodynamics again, because that's the framework that allows us to go from the statistics that we have in the simulations to the observations that we might want to compare with from the experiment. Okay, so what's on the main? Oh, and it's that day again. So we'll, it's about force fields and interaction. So force fields are basically a model that describe how atoms interact in your system. So that's, let's say, the universe, that describes the protein universe, how it's built. There are many different flavors, which I won't go into. I'll just explain the principles to you. In the book has some pointers to different force fields and so on. And if you want to have a more in-depth primer of what force fields are, look up the GROMACS manual, because it says it's a manual for the GROMACS MD software, but it also is a quite good and concise introduction to the molecular dynamics simulations. And we'll go into Newton's equations of motion, because that's what we need to actually be able to do dynamics. So where in Monte Carlo, that Sanna did last week, you have your basically arbitrarily defined rule set, or move set, where you go from one conformation to the other. Here we use physics. So we use Newton's equations of motion to move the protein from one conformation to the other through time, basically. So it's a different principle. A little bit about computational cost and efficiency, and also we'll go into the analysis of dynamics, because running the simulation is sort of the easy part. There's some tricky things to it, but the getting useful information out of it, that's actually quite a lot of work. We'll start with thinking about sampling and convergence, because in convergence here means whether your sampling has converged to the point that the statistics that you have in your simulation corresponds to basically the free energy differences that you would expect experimentally. Because if you don't have this properly done yet, then you know you can't trust all of the statistics that you get from your simulation. This is not new to you, because I know I've been saying it before, and I'm pretty sure Son has mentioned it once or twice during the Monte Carlo lecture, because the same thing goes there. If you're sampling too little, whether it's Monte Carlo or molecular dynamics, your statistics are unreliable. Okay, if we don't run out of time at the end, I'll show you one example where I used molecular dynamics simulations to refine a coarse homology model for a particular enzyme, so you get an idea of how you can use that. Okay, so you all know Newton's the principle of Newton's equation of motion. Action equals reaction, so that means if there's a force acting at a time t, then the system will change, and some small time step later it will be different. Yeah, so that's the basic idea. To put this into perspective, did I show this slide before already? You might have, haven't yet. You might have seen it, because it's also in the book. This is about time scales, but it's also about length scales. So if you talk about atomic motions, then you're all the way down here, and it's about fluctuations of, let's say, individual atoms. And they move in the order of, what's 10 to the minus 15? Anybody knows the name of that? In seconds. This is seconds. This is milli, micro, nano, pico. Yeah, femto. Yeah. I thought it was one of those. Femto. Okay. Yeah. So we're between femto and picoseconds when we talk about atomic fluctuations. If you talk about a whole protein side chain, that's 5 to 10 atoms. They move considerably slower. If you talk about a terminus, like the 5 or 10 N-terminal residues of a protein, that's already a bit bigger, so that moves considerably slower. They were at the order of the nanoseconds. This is similar to a helix, small helix maybe, loops, and then a whole protein domain. And the bigger it is, the slower it moves. That's sort of the natural thing. And to get an idea of these are not like hard figures, but this is just to give you a bit of a feeling of the scales involved. When we talk about atomic fluctuations, it's fractions of an angstrom. Angstrom is 10 to the minus 10 meters. We could have put this in meters actually. The SI unit that is used, for example, in GROMACS is nanometers, and there's 10 angstroms to a nanometer. Right? So this would be like picometers actually. This is about 100th of a nanometer. Yeah, so 10 picometers. Loops and domains moving is on the order of angstroms. I would say maybe 10 angstroms. So maybe the scale is a bit off. Because if you're talking about, I think I made this figure with nanometers in the scale. Somebody redid it for the book and then went to angstroms. Because I would say if you're associating or dissociating two proteins binding, you have to move them a little bit more than 1 nanometer. I would say 10 nanometers or so to get them really not bound. Anyway, so you see the scale of the size scale, the lengths involved, and also the size of the motions that are involved also increases with the increasing size of the stuff that's moving. And to move bigger stuff, you need more time. We'll come back to this in a few minutes after I've explained to you how we use Newton's equations of motion in this section. First, another bit of context. So this is like an overview, and this I looked up the reference for this. I have it. I think it's in the book. I'm not sure, but I should have put it on the slide. But this is like a historical overview of how molecular simulations have grown. It actually started maybe a bit earlier than you expect, in 1936, where they didn't use computers because they have not been invented yet, or at least not in a practical sense. But they just used balls of gelatin to simulate, well, not proteins obviously, but as a model for the noble gas. So you have a box with gelatin balls and you shake it and it behaves in some respects like a gas. Then a bit later, when electronic computers were, I think they were probably still using vacuum tubes, so that's pretty expensive stuff. In the 1950s, oh no, it could be transistors already. Transistors probably. Okay, they were doing Monte Carlo simulations, but still of like something like Arlen or whatever. Really, it doesn't matter actually. They all behave the same. It's just the size and length scales are different. Then it's, I think this is still, this is Monte Carlo, this is still hard spheres, this is Leonard-Jones spheres. We'll come to Leonard-Jones in a minute, because it's one of the models of interaction between atoms. This is a gas phase, where it's easier to get good statistics. Then in the 1960s they went to liquid state, but still noble gas. And then a decade later they were ready to do water. Now, this is not biology yet, but at least we're moving in the right direction, right? But this is this is also a biased overview, because there's lots of other applications of molecular dynamics outside the biological domain. But this looks like it's all moving towards protein simulations. But that's because we're just describing how we got to protein simulation. Also in the 1970s, Andrew McCammon and his group at Scripps in San Diego, they did the first MD simulation of a protein. It was still in vacuum, so it wasn't really a biologically relevant simulation, but that was what they could afford in terms of computational time. They did 10 picoseconds worth of simulation. Then, a decade later, Wilfred van Gunsteren, and you already mentioned his name, because he's one of the sources of this scheme that's used in the courses of Groningen for teaching molecular dynamics. He's retired, but I think he's still active, giving lectures and so. And he was doing the first simulations of the protein in water. And then, quite a while later, it says Daura et al., but it's from the same group. They were doing reversible peptide folding. That's the peptide I showed you in the earlier lectures. And this was really a hallmark, because this for the first time showed that the model is actually able to reproducibly arrive at a certain state. And it wasn't even that important that it was the right state, but just arriving reproducibly at the same state was quite an effect, because if your model is bad, it might just diverge all the time. You just end up in sort of different random states all the time, because you have your balance between entropic effects and enthalpic effects wrong. Yeah, then entropy dominates, then you get random results. So this shows that you don't get random results. Around the same time, with quite a bit of more. Oh, sorry. Yes, this is a different group. They had more luck in funding. They used, I think, 3 months of the world's largest supercomputer at that time to do microsecond simulation of MD protein folding. But it was just a single event, not reversible. I already showed you Shaw et al. Again a decade later, where they could actually do MD reversibly of a small packet. So now we're about a decade later than that, and there has been a lot happening in the meantime. I haven't really kept up to date with all the recent things. There's one really cool paper about where they simulated microsecond dynamics of a whole virus capsule, and they looked at how different lipids in the capsule affect the dynamics, and also I think different protein interactions in the capsule structure that affect the dynamics. These are just some projections. But by the end of this century, we can probably do MD simulations of protein folding as fast as proteins fold in nature. I'm not likely to be around, but we'll see. Okay. So the sort of the I was going to say engine, but that's really Newton's equations. So if Newton's equations are the engine, what is the force field then? It's maybe the roadmap that you're moving on. So this is maybe a definition of the force field. So all the forces that we consider to occur in a mechanical atomic system. So it's not all the forces that occur necessarily. It's all the forces that we consider. Because the more detail we consider about the forces, the more complicated our calculations become, and the more expensive they are. So we have to strike a balance between complexity of the description and the computational efficiency. I could go on about that for half an hour. But okay, so now we have to go on. There should be yes, we'll try. I'll try to sort of give a bit of a structure of what kind of forces there are. There was a remark about the use of symbols or the consistency or inconsistency thereof. I think it was by so we try to use U for potential energy, E for enthalpy, enthalpic energy, V for maybe we use V and U both for potential energy. That's possible. We decided on the scheme last November while updating the book, and I'm not sure if it got it consistent all throughout. Anyway, here we use U. This is potential energy, right? Interaction energy, and the total. So there's three components that we consider. Those are bonded interactions, non-bonded interactions, and others, which we call cross-term. I'll explain a little bit about that in a minute. Do you have any idea what is the distinction between bonded and non-bonded interactions? Sorry?
Atoms close to each other, which have in the bond.
Yeah. So atoms close to each other, certainly if they're in one molecule, so if they're bonded, if there's a chemical bond between them. Let's say all the atoms in the side chain of a protein, they have bonded interactions. And then between molecules, they don't have a chemical. They have chemical interactions, but not a chemical bond. So they have non-bonded interactions. So anybody knows an example of a non-bonded interaction? Electrostatic. Sorry. Van der Waals, yeah, a Dutch Nobel Prize winner, by the way. So yes, and he derived those actually from observations of noble gases. Yeah, so it's actually interesting work, but that's another story. But the cool thing is that they're still useful for proteins. So they were derived from. So that's the power of physics. That you derive interaction potential based on observations of volume and energy changes of noble gases, and then like centuries later, you can use the same potential to simulate the interactions between atoms in a protein. Okay, so in addition to having non-bonded interactions between different molecules, there's also non-bonded interactions between molecules if they're large enough. So a water molecule is too small, all the three atoms are bonded and they don't do anything else with respect to each other. Not in a useful way that we need to care about in the simulations. But your protein molecule, in addition to all the atoms being bonded together in different ways, which I'll explain in a minute, the more distant parts of the protein, so maybe two neighboring side chains, or certainly two side chains from different parts of the chain, they also have electrostatic and van der Waals interactions with each other, right? So bonded interactions are not just between molecules. Non-bonded interactions are not just between molecules; they're also within molecules. But bonded interactions, by definition, are always within one molecule. That's basically what defines a molecule. Okay. So, and the cross terms are when these interactions are not independent. So one of the major assumptions that we need to do to have this forceful description is that we consider each of these interactions to be independent. So if you have an atom that's charged, it interacts with another charged atom, then this interaction does not influence the van der Waals interaction of this atom with a third one. Yes, that's what you're assuming. Which is fair enough assumption in most cases. But if these two atoms are polarizable, then maybe the charge distribution changes because they're interacting with another charged atom, and that might interact, but that will actually affect the van der Waals interaction on the other side. Yeah. So it is an assumption that we need it because otherwise the computations are basically you would have to go to quantum calculations, which are too expensive usually for molecular systems. Okay. And even these, so there's a few interactions of these that are explicitly accounted for in simulation. I won't even go into that because that will take too long. But most of these terms are neglected by most force fields because they're not important. They, yeah, they're not important. Okay. This is what I already said. Pairwise atomic, and also the assumption that goes with the pairwise assumption is that they're additive. So you have a lot of pairwise interactions, and if you add them all up, like here, then you arrive at your total energy and the total interaction energy, and that will that's sufficient to describe your system. Okay. So now, what do these interactions look like in a bit more detail? So first, the bonded ones. The obvious bonded interaction is a bond. Yeah, when two atoms are chemically linked, and this is you can actually implement this in two ways. If it needs to be flexible, you actually use the harmonic potential. So I hope you can recognize the harmonic potential here. So this is your reference distance. So for two carbon atoms, this could be 1.15 angstroms or 0.115 nanometers. And then if your actual distance deviates from that, your potential energy goes up with the square of the deviation. And then there's a force constant that describes how strong this interaction will be. And that depends, of course, on the type of atoms and the type of bond. Because if you have a single bond between two carbons, it's weaker than a double bond. So for a double bond, you need a higher interaction potential. Now, it turns out that many bonds are actually not so flexible as you would get with the harmonic potential. And they're, because of how the atoms actually interact, they're much better described by keeping these distances fixed. And that's, again, a different story that I won't get into, but many force fields actually don't have an explicit term for these bonded interactions because they're fixed. They're actually better described being fixed, which has the added benefit, which we'll come to when we're describing Newton's equation of motions, that you get rid of very high frequency motions, which allows you to take bigger time steps in your integration. We'll come back to it in a few minutes. Okay, the second one is angles, where you have three atoms bound. So maybe this is it could be the three atoms in the backbone. You remember them? First one, N, C alpha, CO. Right? So this could be N, C alpha, CO, and then they should be roughly tetrahedrically oriented around the C alpha, which means an angle of about 109 degrees. But that's flexible. This has to be flexible. This is known if you fix this angle, that it's also very good for your integration time step, but then the backbone of the protein becomes too stiff and it doesn't behave like a protein. This has been researched at the end of the 70s. So you need to have so it needs to be able to fluctuate around a certain angle. So you also here you use this potential. What would be the next bonded interaction? Dihedral, right? You've calculated dihedral. Oh yes. timing is everything, right? Okay, yeah. So dihedrals, and but you can't do a quadratic potential there because a dihedral typically is a rotatable bond, like you have the 5 psi angles in the background. But also side chains have dihedrals where side chains can rotate. And so they have to be circular. So we use superposition of cosine functions to do that, where you get different peaks and values to describe the fact that there are some angles that are more favorable for this dihedral and other angles that are less favorable. It has to do with the fact that if you have 4 atoms and both 2 middle ones is where you rotate, and if the 2 side ones are on the same side, there you can't see it because my fingers are too thin, but if you would draw the radius of the atoms here, it would be something like this. So the first and the fourth atom, they actually touch when you're here. So, and in addition, what's the word I'm looking for? You don't do this, but you do something else. Instead of, yes, thank you. Instead of calculating that directly with a van der Waals interaction, this should couple with the angle. So then you actually you just give the angle potential a high value when it has this angle. And then this one is more favorable, and then usually this one is less favorable. So you get a periodic potential there. Now then there's another one that that we need. That's also a dihedral, but it's called improper dihedral because it's not one that's linked to rotatable bonds, but it's actually linked to non-rotatable bonds. Where do you find non-rotatable bonds?
Double bonds.
Double bonds, yeah. So where do we find them in proteins? The amide bond, yeah, the peptide bond. So you have these. Let me draw that. So N C alpha CO, right? And then you get the next residue, N C alpha CO. This is your peptide plane, right? And these are actually 2 triangles. So 2 planes, dihedral is Greek for 2 planes. Yeah, so it's this angle. It actually has a name, it's called omega. It's not so important because it's usually just 180 degrees. But in the simulation, it doesn't just get 180 degrees magically. You have to put it there. Yeah? So you put actually a dihedral on this plane to make it 180 degrees. Yeah? So this is sort of still a proper dihedral in the sense that it is actually linked to a bond. Yeah? But you also have things like this C alpha, because there is if this is an alanine or a bigger line, you have the C beta here, and then if the hydrogen at the back. The hydrogens are usually not included in the simulation. So then you actually need a potential that keeps these 4 atoms out of the plane in the right angle. So that's what's drawn here. So if this is your N, this is your C alpha, this is your carbonyl C, and this is your C beta, then you can also define, don't try to work it out in your head while looking at this figure. You can go crazy that way. But you can define a dihedral angle actually between these 4 atoms so that you keep this one out of the plane in exactly the right distance. So this is like a tetrahedral arrangement where the 4th surrounding atom that would be at the top here isn't there. Oh. Okay. Then there's another case where you have if you have an aromatic side chain. Sorry. Yeah? Oh, sorry. This is the hexane. Aromatic. This should be planar. Right? And then, so then you actually define a couple of dihedrals, improper actually, dihedrals, with a harmonic potential to keep all these angles so that the aromatic side chain stays planar. Yeah. Okay. This is more detail than you need to know, but now you know what this is. Okay. So there's a lot of detail that you have to put in these protein structures to get them right. Yeah? Unfortunately, people have done that. This is what we call a force field. Yeah. So this is the bonded interactions. Then we get the non-bonded ones. So slow. Is it now the pointer, or is it just my computer being slow? Because with the dihedral it was just slow. I pressed once and then it took like half a minute. Okay, no, now it's just the pointer doing that. Spare batteries. Anti-battery. No. Wrong way around battery. Yay! Oh, now we're moving back on time. Okay. Yay, non-bonded interactions. Okay, so Coulomb's law for interactions between charged particles. So that's like charged side chains, but also polar atoms have a small fractional charge. So let's say water, so the oxygen is slightly negative and the hydrogen atoms are slightly positive. And this is actually, quantum chemically this is not correct, but this is sort of the basis of the hydrogen bond. That these charges are, that these polar atoms have a partial charge. And it's simply the product of both charges divided by the radius, so that's the energy of the interaction. Okay. And then we have the van der Waals interaction, or van der Waals, if you pronounce it the Dutch way. Yes, please. Okay. Which is a little bit more complicated. It's also something divided. Oh, my exponents have gone. This should be squared. Oh no, sorry. This isn't squared. The force is squared, but the potential is just r. This is the exponent is here. Sorry, I thought I should do that. So this is also something divided by r, but this is to the 12th and this is to the 6th. I'm not sure if this is correct. This might be. I am expecting a square there.
I think it's correct.
Hmm?
I think it's correct.
Yeah.
It seems very familiar.
Yeah.
It's the same.
Yeah, I think it's. Yeah,
In the book it's the same.
it's the same. Okay, so at least it's consistent. That's a relief. I'll look it up in the drawings manual because that's what I will trust. Okay. So this one you can imagine, right? It's just 1 over r going down with distance. The van der Waals is the same idea, except because of the higher exponents, it goes down much sharper. And because you have so you have r to the 12th positive, and then you have r to the minus 6 negative. So it first goes down sharply, then it goes back up. Yeah. So that means atoms at a close distance they stick, and at a larger distance they don't feel each other anymore. Yeah. So there's two very simple examples of where you can find van der Waals interactions. So most of you have used Vaseline for different purposes. Sorry. But you know it's sticky, right? That's because the molecules, when they're close enough, they stick. Yeah? And so that's the potential well here, where and if you try to push atoms closer, what happens?
They repel each other.
Yeah, it's this. That's this. That's why it's so hard. Yeah. But this is van der Waals interaction. Atoms moving too close together, and then they push back. Yeah. If you walk into a wall with your head, you can feel it. Okay, so but this is important to understand that this is really, it's so steep, it's like a hard wall. It is actually as hard as a wall, because it's exactly what happens if you walk into a wall. Yeah? Okay. That's enough about the force field, I think. Oh no, we have to put it together because these are just the individual interaction terms. So this is for 2 atoms, 3 atoms, 4 atoms, 4 atoms. This is for pairs of atoms, I and J. Also here, I and J. Sorry, yeah. So this is, so now we still have to put it together, and that looks a little bit like this. So you'd have a sum over all the bonds, where you have a bond interaction for each of them. They might all have different reference distances, and they might all have a different force constant. The same for something's supposed to, yeah. The same for angles. The same for dihedrals. Yes, please, yes. And the same for the improper dihedrals. And then you have the cross terms where one bond might depend on another bond, an angle might depend on another angle. So annoying. A dihedral might depend on another dihedral, or an improper might depend on another improper, and a bond might depend on an angle, and then there's all sorts of other cross terms that you could imagine. Yeah, but these ones you typically don't even need. And oh, it does work. It's just slow. Why is it so slow? And then, so this is these are simple sums. These are just these are double sums. This is also a double sum. Which one is the larger? So this is a sum over I, and for all j's larger than I. So what is that? What would I and j sum over? Atom pairs, yeah? So this I is all atoms, and j is all the other atoms, and then only I, j was larger than I, because if you've done atom 1 with atom 100, you don't have to calculate 100 to 1, because it's the same pair of atoms. Yeah, the interaction will be the same. Actually opposite, but the same. Okay. And how many bonds do you have compared to the number of atoms? More bonds than atoms. If you have 1 atom, no bonds. 2 atoms, how many bonds can you have? 1. If you have 3 atoms, how many bonds can you have? Gosh, you could have 3.
Yeah.
But if you have, let's say, 6 atoms, if this is like a phenol, a separate phenol molecule, then you have 6 atoms, 6 bonds. So typically you have roughly as many bonds as you have atoms. And the same goes for angles and dihedrals and so on. So if you have 1,000 atoms, you'll have roughly 1,000 bonds. But how many items do you have in this sum? If you have 1,000 atoms. Sorry, this one. How many? If you have 1,000 atoms, how many elements in this sum? More than 1,000 or less than 1,000? More than 1,000. How many more than 1,000? Well, 500,000 actually, because you only take. So if 1,000,000, you have the whole matrix of all first atoms and all second atoms, but you only need half the matrix because it will be symmetrical. You have 50 to 800 and 800 to 50 on the other side. Yeah, there will be the same value. You know that. Or actually, the negative of the value, but because I to j and j to I is this. Yeah? Okay, so you only need to calculate one of them. So it's for 1,000 atoms, it's 500,000 interactions. Yeah, so this will be your main source of computational, or actually spending your computational effort.
But aren't like many like neglectable? I mean, some atoms are so far away that
Yeah.
there's no point in calculating it, right?
You don't have, yes, so you don't actually have, because you know this, you've seen this interaction potential. Here. Oh. And at some distance, it becomes negligible. So you think. Okay? So you can say, oh well, beyond, let's say, 1 nanometer or so. But then think again. If you have a distance r and another distance 2r, twice the radius, how many more atoms do you expect at 2r compared to r?
8, maybe?
I don't think, no, it's the surface of the sphere. So the sphere of radius r, and so the amount of atoms that you find at the distance will be proportional to the surface of that sphere. So now you have the surface of a sphere of 2r. So how does the surface of a sphere grow with r?
Squared.
Squared, right? So if you have twice the radius, you've 4 times the, yes? Now, your Coulomb interaction drops with 1 over r. But the total interaction at the distance r is the sum over all the pairs of atoms that you find. So if this goes down linearly with r, and the number of atoms that you find at that distance grows quadratically with r, the total interaction with all the atoms at that distance will keep increasing. Yeah? So it's not as easy as you might hope. So you need a special trick to do that. It does work reasonably well for van der Waals interactions, but also here you do get more particles at a larger distance. So the distance at which you can safely ignore all further interactions is much further out than you might hope. Okay, that's already way too much than what you need to know. We already have this. We already have this. Oh yeah, so now, what we finally have is, so we can ignore these ones, fortunately, because those are also double sums, which ends up with a lot of things. So we have bonds, angles, diagonals, and impropers. They just are basically linear with the number of atoms that you have, and this one is one that you should care for. Yeah, I won't go into all the cool optimization techniques that have been invented to do that accurately but efficiently. There's a lot of that covered in the Gromex manual, and there's a couple of papers from the Gromex group and from some other groups that are developing these kind of methods that are pretty sure, I'm going to put it on my slide, but I'm even more sure that it's in the paper, in the book. Okay. So now we have the force field, that's like the roadmap that we want to move on, and the next step is to use Newton's equations for actually moving around in that. Yeah? And so we first have to define what we move around in. So we have coordinates p and momenta. There's a typo there. Now I have to figure out what p and q were, because I always mix them up. P are the momentum. Okay. I'm just going to fix it straight away, because this is going to be so annoying. P coordinate q. I changed the font last Sunday. Oh, sorry. Last Sunday, and then I think I copied the letter, not just the formatting. Okay, so we have coordinates q and momenta p, and the momenta are just simply the velocity of a particle times the mass, and that's basically almost directly related to the kinetic energy. So it's easier to work with in the equations than just the velocity, because in the end about the energy. Together these are called configuration space, and this is actually what you need to sample, but that's a different story. And we have two components in our energy. The total energy is E, we have a kinetic energy, and we have the potential energy. And yes, So kinetic energy is just a function of the momenta, so by half mv squared or half p squared divided by m. And the potential energy is a function of q, our positions, and the function is actually our force field. Yeah, so the q, all the positions of the atoms are the input to your force field. The output is your potential energy. But there's something even more important coming out of the force field, which is already in the name, which is the forces that we need. So for Monte Carlo, this is fine. Monte Carlo only depends on the energies. So if you have a description of the interactions of your system that gives you energies, then you're happy. For molecular dynamics, because you use Newton's equation of motions, you actually need the forces. And some descriptions of an energy don't allow you to have an associated description of the forces. Okay. And this is just to highlight that the potential energy is actually what you get out of your force field. Now we go to Newton. This is the famous way to write it, F equals m times a, but the way Newton actually wrote it was a partial differential equation where the second derivative of the coordinates are, with respect to time, times the mass equals the force. Yeah? And the nice thing is that this actually, when you can calculate your acceleration, and from your acceleration is actually a change in velocity, and from your velocity is actually a change in coordinates. So the acceleration changes the velocities changes the coordinates, and thereby you can set your whole protein system in motion, literally. Yeah. Okay. And the sum here, I is over all atoms. Okay. And just to highlight, so because I've described the force field previously as energy potentials, and there's a relation between forces and the energy because it's just the first derivative with respect to the distance. So if you look at your van der Waals interaction, or this actually the function that we're showing here is the Lennard-Jones potential, which is an approximation. So this is your potential energy going up, and then the force is actually the steepness of the line. So sorry, I should do it like this. The slope of the line. So here's going down. That means the force is pushing out, and that's the wall pushing back when I go to close distances. If I'm at slightly larger distances, yes. Then the force is actually pulling in. Yeah? So that's your sticky bezel or whatever. Yeah. Okay. Oh, that's enough. That's enough here. Okay. So the principle of Newton's equations is that they conserve energy. They're time reversible. So if you switch all the velocities around to the different, then you move back exactly where you came from. Think about a pendulum. Yeah, if you stop it here, you reverse the velocity, it will just go back and it will move exactly like it was moving together. And it also means it's deterministic. When you know the starting position, then that means all the rest is not a surprise. If you run it, if you calculate it 100 times, you get the same answer 100 times. Yes. So this is the theory. This only works actually. This is also mathematically you can prove that. This only works for 2 atoms. For 3 atoms, small changes in the initial position actually. I'm lost for the word again. They get bigger all the time. There's a word for that. Increase? Yeah, there's an even more stronger word for that. Okay. But so it diverges. That's the word I was looking for. Yeah. So these differences diverge, yeah, and then you get completely different outcomes, even from two very similar style conditions. Okay. And this is true. So this is true for, let's say, celestial mechanics. If you have one moon orbiting a planet, then it's pretty deterministic, although the planet usually is orbiting a sun, so that distorts it a bit. But if you have two moons, like Mars has two moons, they have chaotic orbits, yeah, because of the physics. In our simulations, it's even worse because we don't have the proper physics. We have a numerical approximation of calculating the time evolution of the system. So we also have, in addition to the intrinsic things, we have the numerical errors that accumulate. Okay. I want to do a little bit of maths here. I actually want to prime you with that, and then because this is the way you do the integration, but we'll have more of that on the next slide. This is what I already meant. So it means that actual simulations are not reversible. They don't strictly conserve energy because every rounding error that you make actually either introduces or removes energy. And then some systematic errors that you tend to make in the energy that keeps accumulating. So there's a very pragmatic approach to this because you typically want to simulate not at constant energy anyway, but at constant temperature. So you couple this, you can do what's called coupling to a thermal bath. So you're pretending that your system is immersed in a big bath of water with a constant temperature, and so whenever your system heats up, it will exchange the temperature with the bath, and that means it will overall keep the same temperature. Yeah. It's called recoupling schemes. Basically means that whenever your system heats up, you just scale down all the velocities, and when it gets too cold, which usually doesn't happen, you scale up all the velocities. Not in one step, but gradually. Okay. It's also not fully deterministic, as I already mentioned. Okay, so Newton's equations, their differential equations, they're basically exact. We can solve them for 2 particles. We can't solve them exact for 3 particles, let alone for thousands of atoms. But we can integrate them numerically. And the way this integration is done is by writing a Taylor expansion of Newton's equations. That's just a mathematical trick where you go from a differential equation to a, forgot the name, but basically, yeah, no, but you basically go to a discrete, so in a differential equation, everything is continuous, time is continuous. But in the Taylor expansion, it allows you to actually make a discrete time step. So you make an approximation of what the motion will be after a discrete equation. Differential equation. Difference equation. Yeah. Yes, it's going from a differential equation to a difference equation. So where the time is no longer continuous, but it's a discrete step. And so this, I'm not going to explain how a Taylor expansion works, but I'm just going to show you what you get. So you can then write that your q positions at the next time step, t plus delta t, will be a function of your current coordinates. That makes sense, because that's what you're starting from. Plus 1 over 1 faculty, which is just 1, of the first derivative of your coordinates with respect to t, times your time step, plus 1 over 2 faculty times the second derivative times delta t squared, plus 1 over 3 faculty, third derivative, delta t times to the power 3. And this, if you want to make this exact, you have to increase expand this sum to infinity, because this is 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Yeah, you can do this indefinitely. That's not very computationally efficient. You can truncate, but this fraction is going to go down, which is 3 faculties already. What is it? 6. 4 faculty is 24. Yeah, so this fraction means that each subsequent term will actually have a much smaller effect. In addition, the time step, if your time step is a fraction of a second, then the square of that and the third power and the fourth power are increasingly smaller numbers. So you can sort of safely truncate this series at some point, and here we're truncating it at the third thing. So the first derivative is of course our velocity, second derivative is our acceleration, the third derivative is the change in acceleration. That's already quite detailed, right? And that's, so we'll truncate it there. We don't have a name for the change in acceleration. It's just the third derivative. So then you get this t plus delta t, q, that's positions, this is your velocity, this is your acceleration, and this is your change in acceleration. Yeah? Now the trick that you do is to also write this one for the reverse step. So q minus delta t. And then because you have minus delta t to the power 1 becomes minus delta t squared is plus delta t squared, and delta t to the third power is minus delta t to the third power, because this minus here. And then you can add them up. Yes. So you add up these two equations, then you can simplify it, and then you get a very nice integration scheme, which is known as the Verlet integration scheme. So if you can do that over coffee, I'll be back in 10 minutes. Yes. And feel free to go for coffee as well. But think about this solution, because it's a very nice trick.
sessie niet in beeld.
Ja, nou ja, als ik maar hoorbaar ben.